Hello, everyone, and welcome to this latest webinar from Omdia, brought to you by Informatech. My name is Alan Tatara, Senior Event Manager for the Omdia Webinar team, and I want to thank everyone for joining us. Today, we'll look at getting the right 5G transport technology mix. Our expert panel will uncover what you need to know to migrate successfully to a 5G xHaul architecture. Our webinar is co-presented by Omdia and our partners Anritsu, Fujitsu Network Communications, and Infinera. So before we continue, let me just highlight some of the features that are available for you on our webinar today. So the console that you're looking at, it is completely customizable. So this means you can open, close, move, or even resize any of the windows that you have on your screen and arrange this console any way you choose. Now, at the bottom of your console, you're going to see a number of application widgets. So make sure you check these out during the webinar. But one button I do want to mention is the resource list widget, because this is where you will find additional material about our topic, including the downloadable slide deck from our session today, as well as other valuable resources, including a special report authored by analyst Richard Webb. You could also join us on a conversation via Twitter, and all you have to do is make sure you follow us using the hashtag 5GTransport. We will also have a live Q&A session directly after our presentation, so please remember to submit your questions or comments at any time by using that Q&A window that is on the left side of your screen. Also note that this webinar is being recorded and that the on-demand version will be sent out to you within about 24 hours. And if you experience any technical issues, all you have to do is click on that question mark widget and you will get the answers that you need. All right, so let me take this opportunity to introduce to you our panel. First, leading our discussion is Richard Webb. Richard is the Director of Research Analysis in the Service Provider Technology segment at Omdia. We also have Daniel Gonzalez. Daniel is a Business Development Manager at Anritsu. Also joining us is Joseph Masserino. Joe is a Principal Solutions Architect of Optical Networking at Fujitsu Network Communications. And rounding out our panel, we have Timothy DeWieren. Tim is Senior Director of Solution Marketing at Infinera. So welcome to our speakers. It is a pleasure to have you with us today. So right now, I'm going to turn things over to Richard so we can get started. Richard, over to you.
Okay, thanks very much, Alan. So hello, everyone, and welcome. To start us off, I'm going to run through a few slides just to set the scene a little and to give some context to the focus of our webinar today. So to kick off, let's consider the environment we're in, which is one of transformation on a number of levels. Firstly, one transformation is the evolution from LTE to 5G, non-standalone in the first instance, and then onto standalone architectures. 5G enables flexible and modular RAN architecture with a centralized RAN and virtualized RAN options, and a shift away from LTE's evolved packet core to more of a virtualized core environment for 5G. So that's another transformation. 5G enables greater diversity of network usage in terms of traffic types, services, applications, user types, all of which is adding to the complexity and the demands on the transport network. Services themselves are transforming from the mobile broadband that's been prevalent in LTE to 5G's more enhanced version, and then continuing to evolve onto ultra-low latency communications, massive machine type communications, and so on, all of which continue to place different demands on the network in terms of capacity, latency, network performance, service level agreements, and so on. And in turn, those demands drive requirements for things like network slicing, edge computing, and getting more intelligence and automation into the network. High capacity drives increased densification. So the scaling up of radio endpoints is something we're going to see in later phases of 5G, certainly. Again, adding more complexity to the demands on the transport network. 5G also is going to predominantly use TDD spectrum, and this in itself has different requirements to FDD spectrum, which was mostly used for LTE. And of course, LTE is not going away. The clue is in the name there. It's a long-term evolution, so it will continue to coexist with 5G for the foreseeable future. So operators really need a unified transport platform across LTE, 5G, including macro and small cells, mid-haul, front haul, for different architectural options as well. So great complexity and demands on transport. So let's just have a look at what operators think about this. Here's some data from a survey we did under our IHS market brand in late 2019. And this is a study focused on operator 5G xHaul strategies. We asked operators about their challenges, drivers, technology choices, and so on for the transport network. And in this particular question, we asked what they felt were the biggest challenges to network performance in particular for mobile xHaul. And the chart you can see on screen is how they responded. So no surprise, meeting latency requirements for 5G was the highest rated challenge. Network slicing was also seen as a challenge. Implementing and operating network slices has some complexity still. It's still quite unknown territory, though none of our respondents did not see the benefits of that, but still quite a complex environment. Automation, another challenge, important to support within networks that have to handle more traffic, more applications, more user requirements than ever before. Again, emphasizing that need for more intelligence in the network. Related to this somewhat, you'll see packet-based quality of service, very important in meeting SLA requirements and so on. So without going through every single part of that data set, you can see many different ways in which the network has to perform better to meet 5G demands. So now I'm going to bring in Tim de Weren from Infinera to tell us a little bit more about the landscape for 5G transport and how that is evolving. Tim, over to you.
Awesome. Thank you, Richard. Really good setup. So, look, 5G brings with it many opportunities and challenges, not the least of which, of course, is increasing capacity as we try to interconnect the radio access network with the packet core. In order to be able to cost effectively do that and overcome some of the other challenges Richard set up on the prior slide, we really think collectively we need an all hands on board approach to the transport solution challenge. What do I mean by that? I mean things like intelligent pluggable optics at the edge of the network that can let us cost effectively and operationally simplify the interconnect to the radios and to the radio units. Ethernet-based front haul with time-sensitive networking, so we can get the benefits of Ethernet while also having good timing and good prioritization performance. Optical transport, disaggregated routing, and then the other piece I would just say is we have to keep innovating as well. And so you'll see things like the promise of point to multipoint optics in the future that can also give us a way to potentially re-architect and simplify the network. And so in short, we really need a toolbox and a toolbox-based approach. And that's true even for the deployments within a single service provider, not just amongst different service providers. This toolbox will be needed even within a one service provider based on the variations of wireless deployment that will occur. With that, Richard, back to you.
Okay, thanks very much, Tim. A really nice little taster of some of the things we're going to be touching upon later in today's webinar. So hopefully that sets the scene a little in terms of some of the changes that 5G brings. So now let's take a look at some of the specific challenges that 5G creates for the transport network. I'm going to hand back to Tim just to kick us off and to tell us a little bit more about 5G RAN evolution. And then I'm going to ask Tim to hand on to Joe Mosserino from Fujitsu and then Daniel Gonzalez from Anritsu to follow and talk us through some of the challenges for operators specifically. So Tim, over to you to begin with.
Great. So before we can drive into the transport network, we need to think about what's happening with the radio access network and the core. And in some ways with 4G, when we started at least, life was fairly straightforward in terms of we have a radio, it has all of the RF equipment it needs, plus the electronics it needs, and we're going to connect that to a packet core, and we're going to call that mobile backhaul. However, along came an idea that was perhaps we don't need radios and electronics all packaged together, all in the same geography, everywhere simultaneously, in part because we have people moving around from the suburbs to the core of a city, to the central business district, and maybe the central business district back out to the suburbs or to other locations. And so maybe what we could do is we could centralize the electronics, and we could have radio units out there that were really just the RF portion of the communications. And from that, of course, front haul was born. And so was this idea of disaggregated functional entities with the remote radio head and the broadband unit, which was effectively the electronics or the intelligence. As we take the next step to 5G, though, we learned some things. We learned that if we have to send the raw over-the-air bit stream to the radio unit, that takes a lot of bandwidth. And especially as we think about bigger channels, we think about desire for things like carrier aggregation and MIMO and those things, the bandwidth even explodes even more. So in the case of 5G, we've got the radio unit, the distributed unit, and the centralized unit, and we're mixing those functional blocks up, and we're trying to balance the combination of bandwidth that we need to send with the overall complexity and intelligence that's there, which we'll now take a look at in the next slide. So I've seen this slide done, or a version of this, multiple times in multiple ways. I took my own stab at it, trying to use some color coding and some other visualization to help tell the story. And so what we have is functional hierarchical blocks of things that need to be done between what was the baseband unit and the radio. And in the case of 4G, we balanced that toward the radio was effectively, I'll call it dumb, or had less of the stack in it. And so it really just took the bit stream and put it out over the radio interface. That led to this high front haul bandwidth. And so as we look at 5G, we're looking to pull some functions, like the low-fi portion of the split, back into the radio so that we can balance that complexity versus bandwidth trade-off and enable things like eCPRI type transmission. There's still discussions here about various deployment models, but the O-RAN Alliance and a lot of folks have kind of aligned around this split 7.2x or 7.2, where a portion of the intelligence goes back to the radio and the rest remains with the distributed unit. All of that is just to say that these are functional descriptions of RU, DU, and CU. They do not have to be deployed in a common location, nor do they have to be completely separated and deployed in that manner. And in fact, a mix of that is what will occur as people seek to balance bandwidth, latency, complexity, and achieve their overall service goals. With that, I'm going to hand it over to Joe to take us further here. Joe?
Thank you, Tim. So further on what Tim was saying about the different segments of the network, I'm going to focus on the front haul starting off here, where, as Richard mentioned, in the 5G market trends, new use cases will need low latency to be viable. In the network edge, the closer you get to the cell tower, the more critical latency becomes. So a centralized RAN topology assists in the support of high-performance functions in the RAN, such as carrier and cell site aggregation capabilities, and to add higher performance in those areas as well, but also providing pooling efficiencies by centralizing all the electronics into one location, allowing planners to design their RAN network based on regions instead of individual locations. Proprietary RAN elements limit the support of transport options and the evolution from a legacy 4G to 5G capability. So you want an open RAN capability as well as open transport capabilities, but having these proprietary elements do limit mobile network operators' overall deployment and operations. And finally, on this area, there are challenges in terms of cell sites that have limited front haul or limited footprint and power capabilities, such as deployment of millimeter wave type radios, which in their deployment, they have coverage limitations, and in those coverage limitations, they need to be deployed as a result at lampposts or utility poles or sides of buildings in places that are non-traditional, where you do not have ability to install rack-mounted type of equipment, maybe not even power available for the transport part of the network. The 5G mid-haul and backhaul uses a layer 3 transport for dynamic on-demand connectivity. The traditional router has its limitations in that it consists of an integrated control and data or user plane. This control plane provides the provisioning of VPN slices, self-healing, and OEM support for performance visibility. Impacts to the control plane can cause performance degrade, or in the worst case, an outage of all the VPN slices abstracted on that particular network element, impacting service availability. So with that, let me hand this over to Daniel.
Thank you, Joe. And as mentioned by both of my fellow presenters, 5G transport deployment addresses new challenges uncovered when transitioning from 4G to 5G. That being said, as Tim mentioned in his earlier slide, the architectural change from radio and transport with the introduction of functional splits within the 5G RAN enables providers more control over their bandwidth utilization and complexity through the combination of virtualization and network slicing. So what I'm trying to present here is a brief evolution of the RAN from that distributed architecture that was used in 3G now to centralized in 4G, and then eventually now looking at virtualization in 5G through the use of functional splits. Now, when you combine the network slicing on the virtual infrastructure to support the various 5G use cases and applications that both Joe and Tim mentioned earlier, the challenge becomes when you're deploying these new 5G transport is to take advantage of the virtualization and functional splits and network slicing. But how do you guarantee that network performance for each of those 5G service level agreements, or the SLAs, through the 5G RAN? So let's discuss a little bit about that demand for service level agreements within that new 5G virtual RAN architecture. So what I'm displaying now is what you see on the top of the slide is the physical topology of the RAN. So starting with mobile devices on the left through the core that you see on the right. Now, for simplicity's sake, I broke the physical network demarcation points into the cell site, the hub site, the edge, and then finally the core. Now, although the physical network path remains constant for the transport network, the 5G services will be split into different categories based on performance requirements. So what do I mean by that? For example, let's start with enhanced mobile broadband, or EMBB. Now, this would utilize a higher functional split, such as option 7, similar to what Tim described earlier, for higher bandwidth, but it does have an increased latency associated with it. Now, whereas one of the most challenging ones that we see for 5G is ultra-reliable low-latency communication, or URLLC. That's going to utilize a lower split, which provides more intelligence to that of the RU and DU combined, perhaps at the radio itself, to reduce that latency. And then finally, you have the third commonly categorized application of massive machine type communications. This would be similar to the millions of cellular IoT devices that would be deployed. That does not have the bandwidth or latency requirements as most EMBB or the URLLC applications that I just previously described. And the intelligence can reside for that application, be it massive machine type, to that closer to within the core site. So what does this all mean? This means that the challenge is, how do you provision each one of these and verify that these services meet the expected service level agreement, or SLA, through that same physical 5G transport topology based on the tools implemented by the provider. Now, outside of that, I have a second challenge when facing 5G RAN transport, and that has to do with time and phase synchronization budget for each segment of that network. So in many new transport deployments that you see for 5G NR, specifically addressing TDD or time division duplexing radios, the synchronization is provided through the network utilizing a packet-based timing, such as IEEE Precision Time Protocol, or PTP, instead of or in place of GPS at every node. However, network synchronization is affected by two types of timing error, or TE, which impact the performance and ultimately can impair your 5G nodes. That timing error is broken up in either dynamic or constant time error. Now, each segment of the transport network, starting with the primary reference timing clock, or the PRTC, and Grandmaster, have timing error, and that timing error is cumulative. So the challenge facing operators when deploying the new 5G transport is to determine what is that total timing error through the network, and to verify that that doesn't exceed the total budget. Now, this budget is defined within the 3GPP, and depending on if you're looking at just the transport network, it's 1.1 microseconds total, or when you're looking all the way end-to-end to the mobile device, you're looking at 1.4 microseconds. So with that, that's just a brief summary of the challenges that when deploying 5G transport, and I'm going to hand this back over to Richard. Thank you.
Great, thanks very much, Daniel. A nice overview there of some of the key considerations and challenges in planning the transport network. Before we press on, just a quick reminder, you can submit your questions to us at any point during today's presentation, and we'll do our best to get to as many of those in the live Q&A part of the webinar towards the end of the hour. So please keep those coming. Okay, so we've had a look at some of the problems and challenges. Now we're going to have a look at some of the solutions. And to start us off, I'm going to ask Tim to pick up on the theme of Open RAN a little and tell us firstly how this area of activity is shaping up. Tim, over to you.
Thanks, Richard. So as service providers have thought about the functional split orientation of RU, DU, and CU, and then I've got a 5G core. The other thing that has emerged has been the desire that these particular functions or capabilities could have some consistent behavior, we'll call it, in part so that they could be interoperable, and in part so that I might be able to mix and match some of these functions. And so, and again, with the disaggregation and the functional split orientation, there's just lots of variability that could be there. And so part of what you see the O-RAN Alliance doing and the membership associated with that is trying to define some common splits and some common kind of functional behaviors that could emerge. And a lot of that being driven by a desire to avoid lock-in, a desire for improved economics, and a desire for accelerated innovation so that I can have a vendor perhaps that doesn't make radios, but also could make software for the disaggregated unit and the centralized unit, or vice versa. Maybe I have somebody who just wants to focus on the radio aspect as well. There's been a lot of collaboration with O-RAN Alliance and Telecom Infra Project. Telecom Infra Project has been focused around things like this disaggregated cell site gateway, which is about separation of hardware from software for the routing and kind of first level aggregation. Other activities that are broader, like the disaggregated open routing, Open RAN, and end-to-end network slicing. One of the latest developments was the ONF. I just saw an announcement, I think it was last week, about the ONF's involvement here as well. And they've begun some collaboration with these groups also. Bottom line is kind of this. As service providers push for Open RAN and some interoperability with these functionalities, they also want to ensure that their transport network is open and available as well. And thus you see the Telecom Infra Project and the DCSG project as well, Disaggregated Cell Site Gateway. So it's good that that's happening in theory or in collaboration, but what's happening in the real world? And so I just thought I would cite a few examples here that open transport, or at least as defined with the Disaggregated Cell Site Gateway approach, does appear to have some building momentum. And last year there was an announcement with Telefonica, Germany, embracing this along with some of the other opcos. In addition to that, we actually had a press release last week about expansion of that solution to Telefonica Peru. Also Vodafone in the form of Vodacom in South Africa also had a blog or an announcement that was about that the DCSG solution moving after kind of months of lab trial, moving to live commercial trial and carrying live traffic. And this isn't just clearly an Infinera or EdgeCore thing. Other companies are also involved here, and there have been some other announcements, including a recent one in Taiwan as well, talking about a certain number of DCSG style deployments. I think the takeaway is kind of open and interoperable for both the RAN and the transport is gaining momentum and emerging across service providers and across these organizations. And with that, I'm going to hand this back over to Joe.
Thank you, Tim. A new innovation driving the disaggregation of optical transport system is the smart optics. The smart optics consist of self-tuning DWDM optical pluggables with an in-band channel for remote communications. Used in conjunction with a passive wave division multiplexer, this offers the ability to aggregate services at the cell site and transport over a single fiber core to a central location. At the cell site, the optical pluggable is deployed within the remote radio head or radio unit or Ethernet device, for that matter, and the WDM installs in its own passive outside plant type of remote end is installed in the active optical or a time-sensitive networking platform for remote visibility. This hybrid active-passive transport system overcomes the power and footprint challenges at the millimeter wave radio cell sites while providing automated turn-up and remote OE&M capability through this overall system. Another area that is vital to the front haul transport area is the use of a purpose-built sensitive networking platform that offers a superior low latency performance as compared to repurposed cell site routers. As we heard from Richard at the beginning in terms of ultra-low latency applications, latency is critical and is most critical in that last segment, the front haul segment. Real-world performance testing between purpose-built time-sensitive networking platforms and repurposed routers found a 5x performance improvement in latency and a 75x performance improvement in delay variation, otherwise known as jitter. These performance enhancements result in a 20% greater reach in the transport, which simplifies and expedites the RAN deployment. Disaggregated mid-haul and backhaul elements where the control plane and routing calculations are implemented in the cloud offer performance enhancements and simplified operational integration. In the network slice pieces, each network slice would have own virtual router. The cloud-based routing and control system offers multiple virtual routers abstracted in each edge switch. But unlike traditional routers, the cloud-based control and routing network elements have their own control plane on each virtual router, overcoming a single point of failure that can impact all slices on that network element. The cloud-based routing and control system offers high availability, transport, and simplified operation for multi-service networks. Let me hand this back over to Tim.
Thanks, Joe. Probably everybody on here is familiar with and/or has built or deployed a highly vertically integrated traditional routing solution. From a single vendor, you're going to get the kernel software, you're going to get the protocol stack, you're going to get the hardware, and it's all going to be integrated, custom designed and brought together. That model has served us well as an industry for a very long time. However, with the availability of powerful merchant packet processing silicon to help us with the data plane, we think the time is right to reimagine routing. And what does that look like and what would we do? Well, disaggregated and open routing represents the ability to separate the operating system software, or the IP MPLS protocol stack, if you will, from the underlying white box hardware. It also gives us some other software benefits, including the ability to separate control plane and data plane at a future point. Why would you want to do that? And we think the reason you'd want to do that is you could have more choice in terms of the hardware devices that are available. We think the modularity of a pizza box or a Lego-based approach can improve the economics and also provide the ability for faster, I call it networking velocity, but the ability to get the next round of packet processing silicon into the network faster, because we're not having to do chassis-based sets of upgrades. One obvious question is, I hear you, Tim, but how would that scale? Scalability is achieved by having the ability to stack multiple pizza boxes together. And so you can start with a single one, you can add another pizza box and interconnect them for reliability and or capacity reasons. And if you go beyond a simple stacking of a couple of units, you can insert fabric units and have that horizontally scale to something even larger. All of that looking and acting like a single instance of an individual router. With that, I'm going to hand over to Daniel.
Thank you, Tim. And I just want to simply elaborate on a few points made by both Joe and Tim regarding the transport solutions, such as hardware and software disaggregation. Joe brought up purpose-built routers and the inclusion of O-RAN, all as new options for 5G transport when considering deployment. So in this slide, I'm sharing a segment from the O-RAN specification, which includes the DU to transport SLA, specifically for latency and PDV specifications. I bring this up just to reiterate the point I made earlier in the challenges portion of the presentation on how operators need to verify that 5G applications utilizing functional splits and network slicing. So in this diagram that I'm showing below, the O-RAN specification documents that SLA requirement to enable operators to implement SLA thresholds for latency and PDV for each application. Therefore, it makes it possible to test each SLA in an industry expectation. The O-RAN defines that transport delay between that of the DU and the RU, as well as the processing time for the RU to transmit its symbol over the air. This is all taken into account when defining the SLA, and it's available for operators to implement. So you have this solution available to you today. Continuing from my previous slide, the O-RAN specification also includes the PTP timing distribution use cases over a transport network to meet synchronization requirements. So I presented the network timing error budgets in the earlier section, the challenges portion of this presentation. And now I just want to share with you some of the O-RAN deployment use cases as possible solutions. Now, these are just two use cases presented within O-RAN, and I'll briefly describe the solution, starting with the one on the left. You'll see a grandmaster clock providing that network timing reference through the transport network to the boundary clocks, and then those boundary clocks then feed the 5G nodes. Operators have the choice of either distributing the timing from a central location to the various boundary clocks serving the DUs, as you can see through the mobile front haul in case number 1 on the left, but you also see in the case number 2 on the right utilizes timing as a service, whereas the grandmaster is providing the timing through the mobile backhaul, or through the mobile front haul, as a service to all DUs and RUs directly. In either case, the O-RAN the O-RAN documents these use cases on how 5G synchronization can be achieved through disaggregated network hardware and software functions that were previously described by my two colleagues. And this will to enable interoperability among vendors. And with that, let me hand this back over to Richard. Thank you.
Okay, thanks very much, Daniels. Okay, great. So let's now take a look at deployment applications. What does all this look like from an operator's perspective? How do they implement these solutions? I'm going to ask Joe to kick us off and tell us a little bit more about some of those deployment options. Joe, over to you.
Well, thank you.
Blending 802.1cm TSN for front haul with self-tuning optics enables multiple topology options for the front haul CRAN deployment. MSOs need to roll out their 5G services fast and to maximize market share. Using existing dark fiber as compared to trenching new fiber, which is highly time-consuming, does not always offer the ideal connectivity for the MSO centralized RAN type of configuration. Therefore, having a toolbox of options resolves most of these challenges while expediting deployment within the overall RAN and new services environment. The deployment shows the 5G RAN and transport elements for mid-haul and backhaul. All elements are disaggregated, the RAN using cups or control and user plane separation, and the transport using cloud control and virtual routing. The multi-domain controller or orchestrator blends the RAN and edge switch control planes for end-to-end connectivity. Now, as network slices are abstracted from the edge switches, virtual routers are deployed for connectivity. And then as more slices are needed, more virtual routers are abstracted from those edge switches, providing that end-to-end control and being able to distribute that for the various use cases. I'll turn it over to Tim.
So I thought I would just put a kind of a broader network diagram here about bringing the pieces together that we started all this with, and then and have talked through a chunk of. So inside of a single service provider, how would we look to deploy? Well, at the edge of the network, where we have just radio units, we may use our time-sensitive networked Ethernet switch for that connectivity to deliver eCPRI or CPRI with ROE, radio over Ethernet type of traffic out there. We could use our auto-tunable or our intelligent pluggable optics at, say, 10 gig and 25 gig to connect up not just to the radio units and the sectors of the radio units, but also we then also have the opportunity to offer business services, which is why you see the CPE diagram there. But then there are other deployment locations where we might actually have the combination of RU, DU, and CU all co-deployed, basically like an eNode B from a 4G world or a GNode B in a 5G world. And in that case, we could literally start the backhaul right there, and we could utilize a disaggregated cell site gateway for that particular deployment location, and then we show stacking back further in the network as we need to scale. Overarching all this is some software automation as well. I'll take the software automation forward with this slide, which is with the functional splits, with the disaggregation that's present, with the need for things like slicing and timing and the rest. Clearly, intelligent software automation is a critical part of any type of 5G solution, both helping with the transport network, but also integrating northbound with a broader set of orchestration software that would typically be there, that is also collaborating with the RAN as well as the packet core as well, and that's a key piece. With that, I'm going to hand it over to Daniel to walk us through some SLA verification.
Thank you, Tim. And as Tim just mentioned when discussing this deployment section, the question I want to address is, how does this look in the field, similar to what Tim just mentioned. Again, I'm sharing the physical transport topology above so I can break that down by services and what they would appear like based on the functional splits and the network slicing when you're verifying the SLAs. Now, as you can see on the slide, starting from the left, each SLA requirement for each service differs between one another, and they must be verified end-to-end, first for connectivity, and then second for resiliency when you're adding other services. Keep in mind, and Richard mentioned this earlier in the presentation as part of the slides when discussing what operators are facing, is that this deployment isn't just a standalone. Most of this is being done when there's existing 4G services at the site. So you're trying to balance, how does my existing LTE is performing, how is my existing CPRI-based traffic, and now I'm incorporating this new service levels and these new applications. How are they going to intermix with one another when going over the same physical topology? So the test methodology commonly used in a transport network, Sla Verification, takes both the physical and virtual network segments into account, is the ITU-T Y.1564. This test methodology is available on many devices and field test equipment, and it allows operators to share a common industry standard test result to work with vendors and engineers to define how best to provision their network devices and functions. Now, as I stated in my earlier slides regarding 5G timing error budget and creating a challenge for transport deployment, I then followed that up by sharing several ORAN use cases as possible solutions for operators. Now let's take a look at what that actual deployment looks like of a packet-based timing through a 5G network and determine if that timing error exceeds the maximum budget allowed based on that 5G 3GPP requirement for TDD. Now, to perform this measurement in the field on 5G transport deployment, we recommend verifying that performance at each of the boundary clocks within the transport network. Now, the boundary clocks in this slide, they're noted as TBC, and these can be located within the CRAN. It can be within the mobile front haul, wherever those purpose-built routers or time-sensitive routers, as Joe mentioned earlier, are deployed. And as we've seen earlier with the ORAN timing, these can be based on whichever deployment the operator chooses to select. Now, many operators that are performing G.8275.1 PTP or timing error measurement in the field are measuring two different things. They're measuring both the max timing error that's accumulated through the transport network for each device, but they're also measuring the relative timing error between the cell sites, because this is equally important. You see this measurement displayed on the slide on the right with the measurement, and on the left with the overlapping overlapping cell sites. These measurements are critical during 5G transport deployment moving forward, especially as you're looking at transitioning from the CRAN to a virtual RAN environment or an open RAN environment, depending on where that capability is being added for timing. And now back to Richard for our final section.
Okay, great. Thanks very much, Daniel. A quick reminder to keep those questions coming. We're going to get to the live Q&A in just a moment. But before we do that, I'm going to ask each of our sponsors to spend just a minute telling us a little bit about their own solution. So we'll go alphabetically by sponsor. So we'll take Anritsu first, followed by Fujitsu, and then Infinera. So over to you, Daniel, to kick us off.
Thank you, Richard. So just my last slide here. When installing and provisioning transport equipment to support 5G deployment, Anritsu, recommends the Network Master Pro family of field portable optical transport testers. That's consisting of both the Anritsu MT1000 and the MT1040 Network Master Pro. These are battery-powered, carrier-approved field test equipment supporting all of the 5G transport test requirements that we discussed in today's presentation. This is including end-to-end SLA verification over Ethernet. It supports CIPRI and eCIPRI, fiber verification, as well as network sync timing error measurements for all data rates actually reaching up to 400 gigabits per second. Please feel free to visit anritsu.com, keyword MT1000, for more information on the Network Master family. And now I'll hand it over to Joe with Fujitsu.
Thank you, Daniel.
Fujitsu offers a complete line of open, high-performance, and flexible platforms to address the front-haul, mid-haul, and back-haul transport, along with a complete line of radio units that are working today with virtual networks, virtual RAN networks, to provide a complete overall end-to-end solution in both RAN and transport capabilities. These capabilities can also be fully integrated using our Fujitsu turnkey services, which can provide the install, the tracking, the inventory management, supply chain management, as well as ongoing maintenance of all of your services end-to-end, both the transport and the RAN going forward. So let me just turn this over to Infinera. Tim?
Thanks, Joe. So I'd like to end this part of the presentation where we really began, which was 5G demands a mobile transport toolbox. That toolbox needs to consist of intelligent optics, especially at the edge of the network to simplify operations. It should consist of Ethernet-based front haul solutions, so that we can cost effectively scale and fan out the front haul transport. We also think disaggregated routing has a role to play in terms of expanding the variety of routing options available, while also providing consistency in the protocol stack. And the last piece of that is we also think we can't stop innovating. And while we didn't have a chance in this webinar to talk about multi-point optics, we do think that also holds the promise in the future to provide a way to simplify the network and to have the hub and spoke traffic patterns better aligned to the overall network. And we'll have more to say about that in the future. And with that, I think I'm going to hand it right back to Richard.
Great, Tim, thanks very much. So just going to do a quick recap and then we'll go to our live Q&A. So at the top, I referenced some of the characteristics of 5G architecture, how they bring new challenges in terms of planning, performance, operations. And Tim, Joe, and Daniel all took that forward, talking about the evolution of 5G, how that's driving X-haul transport, and how networks need to be Ethernet-based, enabling carrier aggregation. We looked at how disaggregation and the Open RAN model are driving the need for open transport, and how RAN functional splits and network slicing are placing demands on SLAs and are a useful tool for that. We then also talked about the importance of timing and phase synchronization budgeting for each segment. We explored a number of 5G transport technology solutions, including cloud-based control and routing, providing high service availability and scalability. We talked about reimagining routers and how they can be reimagined with disaggregation, flexible and extensible configurations. And then we talked about some mixed deployment examples, referencing multi-vendor interworking within those open transport environments. And then finally, we looked at the test environment for 5G XHAul, covering end-to-end SLA verification, time error measurement, and so on. So now we're going to take some live questions. So thank you very much for feeding us with those all through today's presentation. I hope you found the content useful, but let's pick up on some of the specifics that you've questioned us about. So first question that I'm going to take for all the panel, and I'll ask everyone to give comment if they wish, is about time-sensitive networking and what advantages it has over traditional optical aggregation in front haul specifically. This is something you talked about, Joe. Perhaps I could come to you about that. You know, what's the great advantage of TSN?
Well, great. Thank you, Richard. That's a great question. In fact, TSN offers a number of enhancements over traditional optical aggregation multiplexing for your transport needs. It's providing those capabilities through that 802.1 CM IEEE standard capability. But essentially, it offers the ability to do transport with a much smaller platform, up to a 75% savings in terms of footprint. Power, also major savings on less equipment needed to transport your services end to end. And it's all based on the TSN standard. There are still options where TSN may be blended with an optical solution, an optical WDM solution, such as millimeter wave interconnect, where the cell site is a utility pole and would have challenges in terms of power or footprint assignments, and that's where a WDM in conjunction with, blended with a TSN solution can also play to provide an end-to-end solution.
Okay, thanks very much, Joe. Tim, Daniel, anything that you wanted to add?
The only thing I would add is just when we were providing front haul with we'll just call it, point-to-point optics or DWDM or CWDM optics, for the most part, we didn't also have the flexibility to offer additional services. We were meeting that need, and that need kind of alone. By deploying a better capable, if you will, Ethernet switch out there, we also have the ability to pick up other types of traffic that we could use in our overall transport network, like some business services traffic or some other that could aggregate into that device. So the one other benefit I would just say is, in addition to serving the 5G and potentially the 4G needs, we also have the ability to then mix into that some other types of traffic for other services that we might be delivering. Otherwise, good.
Great. Thanks, Tim. Okay, so kind of follow-up question looking at time-sensitive networking and PTP deployment. How's that kind of changing the transport equipment environment? I'll come to you on that, Daniel. Is this you seeing this in your role in test and measurement? Are we seeing upgrading or swapping out of non-TSN equipment?
Yeah, thank you, Richard. That's a good question. So we have seen this in most cases. What we're seeing is that operators are reviewing what they currently have. And as I think Tim or Joe mentioned it earlier in the presentation, of the differences between repurposed routers versus purpose-built routers. And one of the significant concerns transitioning from a repurposed router, existing hardware, to a purpose-built is the fact that in order to meet the timing budgets required for network synchronization, that a lot of the hardware is being either replaced or upgraded to new firmware versions to increase the capability. In some cases, the hardware is just not physically capable of meeting these budgets just because, again, it wasn't built with that in mind, or built with the impression that it would be used in a front haul application where the timing sensitivity as well as latency would be the utmost importance. So from a test equipment perspective, what we're being tasked to do is we are performing a lot of these field measurements, or our equipment is being used in these field measurements, specifically when new hardware is being added to meet those timing budgets, because the repurposed routers or network equipment was not capable of meeting the budgets that were required for the operators for the front haul.
Okay, thanks. Tim or Joe, any further comments on that before I go to our next question?
I was just going to say that you see definitely the need for transparent boundary clock and PTP, performance, because folks are looking for a full path solution from grandmaster, to the edge, as Daniel articulated quite well. And increasingly, we started with kind of GPS, clocks and a lot of GPS, but we certainly see folks kind of pulling back from GPS because of jamming, because of, those types of reasons, and GPS almost becoming a fallback, if you will, if they were to lose full-on path sync and timing versus being a primary function like it used to be. I'll pause.
Okay, thanks, Tim. Okay, I'm going to jump onto disaggregated routing now. We've seen some announcements recently about disaggregated cell site gateway deployment announcements, things like that, some early success. What do you think is behind that? Do you think this is the start of a major movement. Tim, you were talking about this.
We hope so. Yeah, time will tell, right? All new kind of technologies take time in incubation. But I do think the mental model of many of the service providers is, if we want open RAN and open radios, we can't have closed transport because the two work against each other and aren't facilitated as much. I'll also just say that I think it makes a lot of sense starting at like the cell site gateway, in part because, as with many things, you can start at the edge of the network and work your way back into the network and toward the core. And so that's kind of an obvious, logical place to start. We have increased capacity needs. We have, timing and synchronization and the things that Daniel has all laid out here. And so it feels like that's an obvious place to start. And the reason is open and more variety and choice from both the hardware and software vendors, modularity, and faster next generation packet silicon to put into the network whenever the next round comes available. That's what I think. Yeah.
Okay. Sure. Thanks, Tim. Joe, any comments to add?
Sure. I would add just to that, and Tim covered that fairly well, is that you also have that in that separation of control plane and user plane, control plane being in the cloud, you do have this separation where your individual virtual routers that are abstracted from your infrastructure, from your edge switches, routers, are basically placed in an environment where they have their own individual control plane. Also, in other types of cloud-based systems, there is the ability to have routing that is also calculated in the cloud and then pushed down to the network elements, and this will also save on performance abilities for the overall network, while maximizing the overall platforms within the infrastructure, the common infrastructure.
Okay. Daniel, anything to add?
Yeah, I'm sorry. Yeah, one brief point to that, and it sounds great, and I completely agree with the transition going to that, where you see that disaggregation of the cell site gateway. But one of the points that I want to make from a testing perspective that we've seen in the field when this deployment is being considered and looking into, and I touched on this briefly earlier in the presentation, but being able to support the existing LTE and CPRI-based traffic you're seeing when they're trying to virtualize that BBU function and having the cell site gateway participate as part of the aggregation portion of that, is being able to determine those services that the LTE and the existing CPRI. You'll see, for example, CPRI translators or CPRI converters, where it's taken the CPRI and eCPRI in order to support that. So I just want to point out that yes, there's definitely a movement in that direction, and there's a lot of benefits there, but there's also a challenge associated with that, because that's also where you see I wouldn't say the choking point, but the point where everything comes together with both the 4G and 5G applications over that cell site aggregation. And that's something that's being tested also in the field, is how is it supporting both the sites that have 4G and 5G converting into that cell site aggregator.
Okay, thanks, Dan. I'm afraid we've just got time for one more question, but our speakers will be able to look at all the questions we've had submitted once they're offline and start responding directly to you over the coming days and weeks. But final question, let's talk about O-RAN white box solutions and what that environment looks like and what the kind of trade-off is between proprietary features and so on. Anyone want to make a few comments around that?
I can add a point to that.
Go ahead. Apparently not, Richard. Go ahead, Joe. Go ahead.
Oh, okay. Sorry about that, Tim. So just one point. We have found that a white box as compared to a purpose-built platform, at least on the front wall side. So, for example, a cell site router white box as compared to a purpose-built platform, where the purpose-built platform will yield a superior latency and packet delay variation performance over that white box, where the white box can supply the overall transport function. It's just the latency and packet delay variation not as good as a built from the ground up, purpose-built type of platform, which results in greater flexibility to the mobile network operators in terms of deployment reach and assignments.
I'd like to add one comment to that, Richard, if you don't mind. Yeah, my comment to that is appreciate what Joe just said there, but I'll just make this statement, which is that's where life kind of started in terms of off-the-shelf white box hardware. Part of the reason we at Infinera took our 15 years of mobile transport and applied it in collaboration with EdgeCore was to help make our DRX30 cell site gateway available, but also then EdgeCore has that same hardware model, and we contributed that design to the OCP TIP community. And part of that was when we first kind of engaged with the white box community, there was a sense of, you know, what about latency? What about timing? What about synchronization? What about these performance behaviors? And at least at Infinera, we've been working to try to educate and help push that industry forward in that manner so that these products do have those types of capabilities, and even committed some of those designs in the case of the DRX30 to the open community for folks to use. Yeah. Thanks. Okay.
Thank you very much. I'm afraid time has beaten us. Thank you very much for staying with us a little bit over the hour, but we really are at time up now. So thanks to Tim and to Daniel and to Joe. I'm going to hand you back now to Alan to wrap up. Alan.
Thank you, Richard. And I do want to thank everyone for participating on our webinar today and for submitting all those questions and comments. As Richard mentioned, we did receive a very large number of those, and our panel will be following up with you via email afterward. I do want to thank Richard for leading our discussion today, as well as for Daniel, Joe, and Tim for sharing your expertise with us as well. So an archived version of this webinar will be made available shortly. In fact, we'll be sending you a follow-up email on how to access that archive, or you can simply use that same link that we sent you earlier. Feel free to come back, view the session again, or even share it with your colleagues. A short survey is going to pop up at the conclusion of this webinar, so please take a few moments to fill that out. And continue to follow us on Twitter and LinkedIn for information on future webinars from Omdia, brought to you by Informatech. So again, thank you for joining us, and have a great rest of your day.